Hey everybody, your day 3 lesson is basically coming from section 10.6. This is all about what we call secant lines and tangent lines and how they interact to form angles. Okay. The assignment for today was kind of a group assignment. This is it right here. You can download this from Canvas. I have a PDF copy there. And I'm going to help you work through this and do some example problems from this. This is the in-class assignment, and it was kind of doubled as the homework. Most people were able to finish this in class or get pretty close to finishing it. And if you weren't here in class, I'll kind of help you get started. The very first thing I want to talk about is just what a secant is, and we talked about what a tangent is. So let me just kind of draw a little image for you here. This is kind of silly, but this is the way I explain secants, tangents, and how they're related. So imagine you have like a watermelon here, and you're doing target practice and you're shooting arrows at this watermelon. A lot of the arrows are going to go into the watermelon, through the watermelon, and out the other side. So, you know, stuff like this, right? Okay, that's called a secant line. A secant line is a line that enters and exits the circle. It hits the circle at 2 points. So it kind of comes in this way and it goes out there. An entrance wound and an exit wound, if you want to think of it that way. Okay, now if you ignore the lines and just look at the inside of the circle, we know these lines or these segments, are called chords if they have endpoints on the circle. But if we consider the full line going in either direction, we call those secants. Okay. Now a tangent line is a little bit different because a tangent line only hits the circle in one place, not two. So imagine there's a little ant camped out on the top of that watermelon, and you're such a good shot that you can knock off that ant and just barely touch the tip of the watermelon in just one spot without, the arrow going in and out of the watermelon. So this guy's called a tangent line. Okay. Now secants and tangent lines can meet to form different kinds of angles. So for example, if you had a secant line going like this, and then you had a tangent line going like this, you got an angle here, right? And we're going to talk about those angle relationships. Whenever a secant line and a tangent line, or two tangent lines or two secant lines, whenever they intersect, we end up with some angle relationships that we want to know about. And that's what this assignment is all about. Okay, so I'm going to walk you through some of these theorems. I'm going to point out where they are. You will write them down on your own, and we'll look at some example problems. The first theorem you're going to look at, and this is for number 1 here, is you're going to look at theorem 10.12. Okay, it's on page 561, and it says, include the figure in the example that's listed. So let's take a look at that theorem here. Okay. So it says if two secants intersect in the interior of a circle, then the measure of an angle formed is 1/2 the sum of the measure of its arcs intercepted by the angle and its vertical angle. Well, that's a little wordy. So let's talk about what that means and break it down. You're going to write that down, but we will, kind of discuss. So first off, here's a secant. Here's another secant. Okay? Those guys intersect. Now, what we know from experience is that this angle that's called angle 1 is going to match this angle, which doesn't have a number, because these are vertical angles, right? These guys have to be the same. What they're talking about then, the arcs that they're talking about, are the arcs that correspond to those two angles, right? The angles are the same, but notice this arc is smaller than this arc. If you look at this example, what this is saying is it says 1/2 times AC plus BD equals the measure of this angle. Think about that for a second. You add two arc measures together and multiply by 1/2. That's like an average, right? If you had two test scores and you added them together and you divided by 2, that would be your test average. So essentially what you're doing is you're averaging this arc and this arc, the measurement of these two arcs, to get this angle. And we also know that this angle is going to be exactly the same angle. Okay? If you look at the other two, right, because you also have these guys, this angle, angle 2, will have to be congruent to this angle that doesn't have a number. these will be congruent because they're vertical angles. To get that angle, though, what you're going to do is you're going to take AD and you're going to add it to BC, right? And then you're going to multiply it by a half or divide by 2. In other words, average this one and this one, average those two arcs to get the angle inside. And again, these are going to match. Okay? If you look at example 1 on the next page, you'll see what's going on there. So take a look at what they have here. You got 20 degrees, you got 30 degrees. And what they're going to do is they're going to average those two arc measures, right? They're going to do 30 plus 20 divided by 2, or 1/2 times 30 plus 20. Okay? 30 plus 20 is 50, so half of 50 is 25. So the measure of angle 1 is 25. That's also the measure of this one, 25. Okay? And then they're just using linear pair to find this guy. So since these two form a linear pair, if you do 180 minus this 25, you get angle 2. That's what's going on. Okay, let's do an example of that. We'll write that down, and maybe this will help you out. Okay, so number 1 was just to write them the theorem and include the examples to just kind of word for word what's in there. Okay, we're going to come back to number 2 in just a second, but let's look at number 3. Okay, draw a new figure as an example and use your own specific angle measurements. So let's just kind of unpack this. Here's a circle, right? We're going to draw two intersecting secants. Okay? Now let's label this arc measure and this arc measure. We don't necessarily know what they are, but let's just pick something reasonable. Obviously they're less than 90, so let's pick something that makes sense. Let's call this guy 40 degrees, and this one has to be bigger, so let's just call it 70 degrees, right? I'm just making this up as an example. Now what we know is we can find this angle or this angle if we average those two guys, okay? So 40 plus 70 times a half, or 40 plus 70 divided by 2. So that's going to be half of 110, which is equal to 55 degrees. Okay? What that means is this guy's 55 and this guy's 55. Okay? That's what the theorem says. The wording, can be a little bit tricky, but we're talking about these arcs, these intercepted arcs, and averaging them to get these. Okay. Now, you might be thinking to yourself for just a second, hold on a second, Mr. Lowry. If this is 55, this must be 55. And if this is 55, this must be 55. Because we had that idea about, central angles equaling their arc measures, right? So, kind of going back to just kind of scratch paper here. We know that if this guy is, let's say, 45 degrees, then this guy has to be 45 degrees. So what gives? Like, what's the problem here? Why are we running into an issue? Or why is it not that case? Well, notice that these are not central angles. Okay, central angles is when the intersection is in the middle. So this looks like something that's similar, but it's not actually the same thing. It's kind of related, but not exactly. So let's go over to the example again, because this is what number 2 is asking. If we look at example number 2, why isn't angle number 1 equal to AC? Why can't we just say that AC equals the measure of angle 1? The reason why is because this is not a central angle. If it was, we could say that, right? So let's draw that out a case that would work. Okay, so let's say you got this guy, right? And this is angle 1, and this is AC. In that case, they would be the same because it's a central angle. But this guy is not a central angle because that is not the center of the circle. Okay, so that's kind of the difference. What we talked about in class was kind of a concept map to help keep track of all this information. And so if you want to make one of these, you can definitely do that. I would recommend it. So let's talk about some things that we know. Okay, so I've divided this this piece of paper into 3 different categories. So in this category, I'm going to write stuff about angles where the vertex is inside the circle, here's where the vertex is on the circle, and here's where the vertex is outside the circle. Okay? Let's just start with the new thing that we just added. So theorem 10.12 is basically going to say something like this. We're going to average the arcs to get the angles inside. So I'm going to draw a secant here. I'm going to draw another secant. Now notice that this is not a central angle. None of these are central angles because this is not the center of the circle. Okay, but I'm gonna put an example here and talk about what we know. So once again, if I know this arc and this arc, I can average them to find the middle. Let's call this guy. That looks like it's about 50 degrees maybe, and let's call this one 30 degrees. Okay, we're talking about the arc measure. Okay, if I average those, 50 plus 30 is 80, right? And then divide by 2, that's going to give me 40 for this guy and 40 for this guy. Okay, so make sure you can see that. It's kind of small. All right, that's an example. So when I'm using this theorem, what I'm thinking of is average. Okay, if the vertex is inside the circle, average the intercepted arcs to get the inside angle measure. Okay, now let's connect that to idea we already know. Okay, so here's a vertex in the circle. Now what we have here, and that we've already studied, is a special case. So we're going to do special case central angles. We don't have to have central angles to use theorem 10.12, right? These are not central angles. But we can have central angles and it will still work. Okay, let me give you an example of that. Let's say we have 2 diameters. Okay, now these are central angles. And let's say that this guy was 50 degrees and this guy's 50 degrees. Okay, what happens if you average 50 and 50? Well, 50 plus 50 is 100, and then you divide that by 2, and you get 50. So that means this guy's 50 degrees and this guy's 50 degrees. So it still works, right? This theorem, average the intercepted arcs to get the inside angle, it still works for central angles. And now we can see, oh yeah, this makes sense. Okay, so 50, 50, all right, the arc measure is the same as the central angle, right? The reason why these don't match is because this is not a central angle. Okay. So this is connecting a new idea to something that we already knew, so that we can, store that information in the same place in our brain. Okay, so both of these cases are when the vertex is inside the circle. All right, let's take a look at a couple example problems and make sure we got that dialed in. Okay, so number 2, we know the measure of a central angle is equal to the measure of its intercepted arc. Why is measure of angle 1 not equal to measure of angle AC in the figure you drew in this figure? Well, again, because angle 1 is not a central angle. That's why. All right, now let's look at a couple of these problems here using that theorem. So these are going to be using theorem 10.12. Okay, 160 plus 50 divided by 2 or multiplied by a half will give you this angle. So 160 plus 50 times a half, or divided by 2, right? Those are the same thing. So half of 210 equals 105. Okay, so this guy's 105, and also this angle right here would also be 105, both these vertical angles. Okay, similar thing here. Pretty basic on number 5. Same idea as number 4. Now number 6 is a little bit different because we actually don't know the arc measure. And so if I don't have that arc measure, I'm just going to call this guy x because I don't know what it is. What I do know is if I add this arc and this arc together, 50 plus x, and multiply those two things by a half, I get that angle, which is 85 degrees. So notice I have an equation now that I can solve for x. Now there's a couple ways to do this. I can distribute that 1/2 to both of these terms, or the easier thing to do is just multiply both sides by 2, because the 2 and the 1/2 cancel, give you a 1. So 50 plus x is equal to 85 times 2, which would be 170. Okay, subtract 50 from both sides, and x is equal to 120 degrees. Okay, so if you wanted to double check, 50 plus 120, that's 170. Divide that in half, that's 85. Check. Similar on number 7. Okay, next we're going to look at theorem 10.13. Okay, this one doesn't have a super good picture to go with it, and there's an example right under it, but that is almost a little bit misleading. So let's look at 10.13. Okay, this is what you're going to write in number 8. Right? Write down theorem 10.13 from your geometry book. It wants you to draw a figure to use as your own example, and then compare and contrast this with another theorem. Let's take a look. If a secant and a tangent intersect at a point of tangency, then the measure of each angle formed is 1/2 the measure of its intercepted arc. Okay, so you can kind of see that here, right? You got a secant and you got a tangent right here, here and here, and they form this angle. Okay, so this angle is half the measure of this red arc. Or in other words, this red arc is double the measure of this angle. Okay, that's what we're talking about. Now there's a kind of an example down here, but this is an example problem, and really what we want to know is like that this angle right here is half of this arc, or this arc is double this angle. There's a little bit of problem solving. They didn't actually give you all the pieces, you know, that you would normally see for like a good example of this theorem, but you can solve for the different pieces. So let's make our own example. And yeah, we'll use that. Now you're going to write this down. I'm not going to write it. It's right there in the textbook. You can find that. But let's draw our own figure. Okay, so we're talking about a secant and a tangent line intersecting at a point of tangency. So here's a tangent line. I'm just going to draw part of it, right? Only hits the circle in one place. And then let's draw a secant. Okay, that's what we're talking about. So here I have an angle, and that angle is half the measure of this arc. Or another way to say that is that this guy is double the angle. So if the angle was measured, let's say 70 degrees, then this arc is 140 degrees. Okay. Now that should look a little bit familiar because we have another thing that looks really similar to that. Okay. And if you go back and look at page 544, theorem 10.5 is about inscribed angles. Let's take a look at that. Sorry. Okay, so the inscribed angle theorem says if an angle is inscribed in a circle, then the measure of the angle is 1/2 the measure of its intercepted arc, or the arc is double the angle. That sounds really familiar, right? It sounds like almost the same. The difference is here you have two secant lines, and in the other one it was a secant and a tangent. But the angle arc relationship is actually the same. Okay, so how are they similar? How are they different? Well, they both have a vertex of the angle on the circle, right? They both have the same relationship where the angle is half the arc or the arc is double the angle measure. The difference is that one of them is a secant and a tangent, and the other one is two secants. Okay, so let me just draw that out for you. So one of them is, there's the vertex, right? Secant, secant. That's an inscribed angle. Okay, secant, tangent. Doesn't have a special name, but it's a different kind of angle. However, they both have a vertex on the circle, and the angle arc relationship is the same. Double the angle to get the arc, double the angle to get the arc. Half the arc to get the angle, half the arc to get the angle. Okay, again, it's kind of useful to keep those things kind of connected. So I'm going to go back to my concept map, okay, and we're going to talk about things where we had a vertex on a circle. Okay, so let's start with the new one. Okay, we're going to put a point on here, vertex on the circle, and we're going to start by drawing a secant line. So from this point, we're just going to come out here like that. Okay, now what we want from there is we want a tangent line coming off of it. Something like that. That's not perfect, but you get the idea. Okay, so what we know here is that this angle is half of this arc measure, or this arc measure is double this angle. So let's just, we can put like an x degrees, that's this full angle here, and then out here, this whole guy, this arc measure, is going to be 2x degrees, or double. Okay, and this is theorem 10.13. That's what it says. Okay, now connect that in your brain to a very similar idea about inscribed angles that you already know. So let's do 10.5 inscribed angles. And it's like not even learning, it's almost like you're not even learning a new fact. It's just like you're connecting it to this other fact that was similar. So log these in the same category in your brain. So let's start with a vertex on the circle again, but this time we're going to do 2 secant lines. Okay. The relationship is the same. If this guy's x degrees, then this guy's 2x degrees. Right? So when I think of the vertex being inside the circle, I think of this average the two arcs to get this guy. When I think of these two relationships, vertex on the circle, I think half or double. Half the arc to get the angle, double the angle to get the arc. So I write here, this is my half or double relationship. This is my average relationship. Okay? All right, let's take a look at some problems there and in your packet and see what we can do. Okay, number 11, pretty easy. We got the secant and this tangent, and they make an angle of 55 degrees. So how do I find the arc measure? I take 55 degrees, and I multiply it by 2, and I get 110 degrees. Boom, done. So double the angle measure. Okay, now if you look at 13, this is actually an inscribed angle. So notice we got vertex on the circle, but it's not this is not an inscribed angle. It's a secant and a tangent. This one is 2 secants. Relationship here is the same though. Double the angle, so 86 plus 1 times 2, and that's going to equal the arc measure. Okay. Now we're going to solve this equation here now that we have it set up, but this is going to give us 172x plus 2 equals 175x minus 1. So if we group all the x's on the right, we're going to get 3x, and then we move all the numbers to the left, we're going to get 3. So it looks like x is equal to 1, which makes this guy 87 degrees, and this guy 174 degrees. And see, 87 times 2 better be 174. So I'm just going to verify that really quick. We got 4, 1, 16. Yep, that works. So if I double 87, I get 174. Okay. All right, let's look at another one with an equation. Okay, 15. So this looks a little bit new, but again, the relationship is the same. The angle formed, if the vertex is on the circle, the angle formed is half the measure of the arc, or the arc is double the angle. So I'm going to take the angle here and double it, and I'm going to set that equal to the arc measure. So 18x minus 12 equals 17x minus 3. Don't forget to distribute the 2. If you group all the x's on the left, you're going to have just a regular x. If you group all the numbers on the right, you're going to have a 9. So x is equal to 9. We wanted to find STU. Sorry, that's angle STU. So if we plug that 9 back in here, we're going to get 81 minus 6, which I think is 75 degrees. So 9 times 9 is 81 minus 6 should be 75. And then back over here, of course, we wanted QPR, that angle. We found that that was 87. So I kind of get excited as I'm going through here to solve, and sometimes I forget to check what I'm actually looking for, so that's a good thing to do. All right, that's how you kind of use that theorem. The last theorem, it looks kind of scary because there's so many parts to it. So let's take a look at that. That is theorem 10.14. So it says if two secants, a secant and a tangent, or two tangents intersect in an exterior of a circle, then the measure of the angle formed is 1/2 the positive difference of the measures of the intercepted arcs. Okay, that's kind of a mouthful, so let's kind of interpret that and talk about what it means. What they're doing here is they're saying that they're taking arc DE, the bigger arc, and they're subtracting BC, the smaller arc, and then they're like dividing it by 2 or multiplying it by 1/2, and then they get that angle. Okay? Now you might be thinking like, oh, there's 3 things to memorize for this situation, and there's actually only one. The main thing that you want to notice here is that for each of these cases, the vertex of the angle is outside the circle. Okay? Whenever that's the case, the relationship is the same. Notice these all look very similar. If you take the big arc and you subtract the little arc, now we're talking about the intercepted arcs, of course, the big intercepted arc minus the little intersected arc, and you multiply that by 1/2, you're going to get the angle measure. Okay? Sorry, I think I messed that up. Once again, the big intercepted arc minus the little intercepted arc, and then multiply by 1/2, or divide by 2. That's true for all 3 of these. Okay? So you're going to write it down in your worksheet right here, right? Include an example of those 3 different scenarios, and then realize that what they all have in common is that the vertex is outside of the circle. So really, you don't have to remember 3 facts for these. You only have to remember 1 fact for these. So let's kind of put that in our mental map. Okay? All right, so we got 3 different scenarios. We're talking about theorem 10.14 here. Lost my, there it is. Okay, so the first scenario is we got, let's say, secant, secant. Okay? We have an exterior point, though, because vertex is out to the circle. That's this whole column, vertex out to the circle. Okay, so secant, secant. Okay, that's one scenario. Another scenario is that we have secant and then a tangent. So we're going to try to do our best to draw a tangent line here. Oops. Not too bad. Okay, and then we have tangent, tangent. Okay, so pick an exterior point. We'll do a tangent, and then we'll do another tangent. Sorry, my tangent line didn't look super good. But you get the idea. The relationship here is always the same. We're going to take the larger intercepted arc minus the smaller intercepted arc, multiply by 1/2 or divide by 2, and that's how you get this angle. Okay? Take the larger intercepted arc, subtract the smaller intercepted arc, multiply by 1/2 or divide by 2, and you get the angle. The larger intercepted arc minus the smaller intercepted arc, multiply by 1/2 or divide by 2. Okay? So this is kind of how I think of it. Big arc minus small arc times 1/2. So that's a little bit nicer than this, right? I mean, this is totally true. And if you're a formula person and you see that and that makes sense to you, great. I like to think of big arc minus small arc divided by 2 or times 1/2. Okay, and that's the same for all of these. So when you look at your mental map here, your concept map, you're like, okay, cool. I actually already knew this one. This is kind of similar. It's just they're not central angles. And the key here is average. right? If the vertex of the angles that we're talking about is inside the circle, just average the two arcs to get the angle measure. Okay, now remember, sometimes they can be central angles, but a lot of times they're not. Okay, now this is true for central angles, that the angle has to match the arc measure. Okay, not so in this one, again, because this is not a central angle. Okay, what about if the vertex is on the circle? Well, again, we already knew this fact. We already knew about inscribed angles. So we just kind of keep the same relationship. Okay, this is not an inscribed angle, but it is a vertex on the circle. The relationship is the same. Double the angle to get the arc, half the arc to get the angle. Okay, these guys are all kind of new, but what they all have in common is the vertex of the angle that we're talking about is outside the circle. And whenever that's the case, you take the big arc, you subtract the small arc, and you divide by 2. Now, it's not just any arc, right? It's the intercepted arc, right? The arc that the angle kind of creates. So the big intercepted arc minus the small intercepted arc, either divide by 2 or multiply by 1/2, and you get that angle measure. Okay, so that's kind of my mental map. That's how I organize it in my brain, so that instead of memorizing 1, 2, 3, 4, 5, 6, 7 different cases, I really only have to know 3. Okay, let's go back and take a look at some of these problems on your worksheet. Okay, first up, you got, we want to find this angle. Okay, so big arc minus small arc times 1/2, or divided by 2. Let me zoom in for you. So 167 minus 95, and we're going to multiply that by 1/2 or divide by 2. Those are equivalent. So that's going to be 72, half of 72, which is going to give you 36. So question mark is 36 degrees. All right. Now, some of these are a little tricky. The tangent ones especially are kind of tricky because you're like, well, what's the other arc, right? You're like, well, here's an arc, and here's an arc, but I have 2 unknowns. Consider this. If it's a tangent, the points of tangency kind of break your whole full circle up into 2 pieces. So if I want to find this arc measure, it's just 360 minus 235. So 360 minus 235 is going to equal 125. So that's this guy. Now that's not what we wanted to find. That's the arc measure, this little arc measure. We want to find the measure of angle V. But what we need to do is we need to take the big arc and subtract the little arc, and then multiply by 1/2 or divide by 2. So 1/2 times 110 equals 55 degrees. So that's 55 degrees. Okay, now I didn't mention this earlier, but I did include the answer key with basically all the ones where you're solving. Not any of the definition ones, because you guys can do that. So let's just, make sure that we're doing the right thing here. So 19, which is supposed to be 36, 21 was supposed to be 55. 36, 55. So as you're going through that, use the answer key to help check that you know what you're doing, because we're going to have a test coming up soon, and this stuff is going to be on the test. We haven't taken a quiz on it yet. It's just kind of the last little bit, and so it's kind of going on the test without, any quiz practice. So make sure you know these. Okay, last one we're going to do is 23. Now, there's a couple things on this that make this a little bit tricky. So let me kind of walk you through that. The concept is the same. It's the big arc minus the small arc divided by 2 or times 1/2 to get the angle. So we can set up an equation here. The big arc is 19x plus 11. We want to subtract the little arc, and that arc measure is 10x plus 4. Okay, where a lot of people are going to go wrong here is that if you're subtracting a binomial, you got to do it like this, right? 2 terms minus 2 terms. So I'm subtracting this thing in parentheses. And so we're going to have to like distribute that negative number. Okay, so big arc minus small arc, that's how you do it. Then we got to either divide by 2 or multiply by 1/2. And when we do that, we're supposed to get the angle measure, which in this case would be 35 degrees. So that's what we got going on. The first thing we're going to do here is multiply both sides by 2 to get rid of that half. So if I multiply the left by 2, this is gone. If I multiply by the right by 2, I'm going to get 70. So let me rewrite. 19x. Sorry, I got to move my paper a little bit. 19x plus 11 minus 10x minus 4. Okay, remember, distribute that negative. Okay, this is going to throw everybody off, or a lot of people off. Okay, 35 times 2 is 70. Let's combine our like terms and solve for x. So 9x when we combine like terms plus 7 when we combine the constants equals 70. Subtract 7 from both sides and you get 9x equals 63. Divide both sides by 9, you get x equals 7. And we're trying to find the measure of VU. Okay? So the last thing we need to do is we need to actually kind of jump in there and find all the arc measures. So if I plug 7 in here, I can find like this arc, and I plug in the other one and I find this arc, and then this is the last missing piece. And remember, the full circle is 360. So let's plug in the 7 and get our 2 arc measures that we have. So 19 times 7 plus 11. Okay, that makes this guy 144. Okay, then we have 10 times 7 plus 4. That makes this guy 74. That's the arc, not the angle. Okay, and then the full thing is 360. So this plus this, and then subtract it from 360. So this is a little bit disorganized because I ran out of room, and ideally you show this as a step-by-step. We do have kind of step-by-step going in here. I should have started up here though. So let's go kind of back up here. And we got 144, this guy, plus 74, this guy. Okay, that's 218. And then we're going to do 360 minus 218. And that's 142. Okay, so the measure of arc VU should be 142. Let's just double check that really quick. Okay, that was kind of a tricky one. Lots to consider. Again, I think the trickiest part of this is this guy. Right? When you subtract a binomial, subtract it as like a full quantity and distribute the negative to both pieces, with that subtraction basically. Getting the x after that is not too hard, but then actually going back, plugging it in, and solving for the measure of VU is a little bit tricky as well. Okay, so practice, practice, practice. You're going to need to know this stuff for the test. This is the only real assignment that that we're going to do on this stuff before you have to know it for a test. So make sure you go through that. Check your answers as you go. If you're super, super stumped on something and you can't figure it out, let me know, and I can see if I can help you before the test. If you'd like, you can add this to your notes. This is probably what I would do. This is how I categorize this in my mind, how I, keep these concepts straight and kind of link things that are related. So feel free to jot that down so you can use that on your test. Okay, thanks so much. Good luck on your tests. Study hard. Don't forget to go back and take Unit 5 Quiz 1. Practice. Make sure you got those concepts dialed in, and do all the review that you need to before you take that test so you can do well. Thanks.